The question is, could you show us how to use calculus to find geometric properties for a triangle? Let's go ahead and first define just exactly what is it that we want to do here. We have a triangle like shown in this picture. We will take this as the base of the triangle and the distance perpendicular to that as the height, h. First we want to find the distance to the centroid C along the height from the base. So that will be y0 marked in this picture. Then we want to find the second moment of inertia of this triangle about the axis x, which passes through the centroid C and parallel to the base. Among the different coordinate systems we have, like Cartesian, cylindrical and spherical, Cartesian is the best to handle this problem because the boundaries of a triangle consist of straight line, right? Straight lines are better represented in a Cartesian coordinate system. So this is what I'm going to do. I'm going to place a 2D Cartesian coordinate system right at this point. Even within this framework, there are a couple of different ways to define the differential element. For example, I could split this triangle into two parts by cutting it through a vertical line that passes through the vertex here. You take the left side and the right side and consider them as two separate entities. The inclined boundaries in each of these entities, like this one and this one, can be represented by mathematical functions. Then you define two separate strip differential elements for each of the two triangles and perform the integration. The procedure is a little lengthy, but you'll get to the same results. So here I'm following a slight variation of that. Instead of dividing it into two separate entities, I'm going to consider this as a single triangle. This is my differential element, a strip differential element. The strip is at a distance of y along the y-axis and has a width of dy. If I can find x0, then the differential area dA would be simply x0 multiplied by dy. I use the proportionality rule to achieve this. You can see this triangle right there, little triangle, and the big triangle are similar, right? And therefore, x0 divided by b must be equal to h minus y divided by h. Rearranging it, we get this expression for x0 as a function of y. Here's the equation for finding the centroidal distance y0. Integral of y times dA divided by integral of dA. The term in the denominator is the area of the triangle, right? Which we know as half times base times height, right? Half times b times h. But in the spirit of using calculus, we'll do that using calculus as well. And in these expressions, I use this for dA, where x0 is given by this expression. To avoid confusions, I simplified a little bit further before I integrated it. Now you should be able to follow these steps fairly easily. Integral of y is y squared over 2. Integral of y squared is y cubed over 3. Integral of a constant b is simply b times y. Integral of y here is y squared over 2, right? Now you apply the limits from 0 to h, and we end up having a value of h over 3 for y0. In other words, the centroid C lies at a distance of 1/3 of the height from the base. And I'm pretty sure many of you remember this, right? Also note that the expression that we have in the denominator is supposed to be the area of the triangle, right? We did end up having half times base times height for that. Now on to our second part, where we want to find the second moment of inertia about an axis that passes through the centroid. And here this is the x-axis. It not only passes through the centroid, but it's also parallel to the base. Now, where you place the y-axis is immaterial. You will get the same result regardless of whether you place it here or here or here or anywhere. Alright? So just for convenience, I've decided to place it right there. Just like we did in the earlier slide, I found x0 as a function of y using the proportionality rule. The main difference between what we did there and this is that the y-axis is now placed over here, right? So therefore this distance is y, not starting from the base. It starts from the centroid. Therefore the height of this little triangle, this distance, is 2/3 h minus y, right? And that gives us this expression for x naught. dA, the area of the differential element, is x naught times dy. Now you remember the definition of the second moment of inertia, right? Ix equals integral of y squared times dA. Here the equation after substituting this for dA. Now note the limits. The integration needs to be carried out over the entire area of the triangle, right? And therefore y must go from minus h over 3 all the way to 2/3 h. You can easily follow the remaining steps, so I'll let you do that. The expression we get for ix is 1 over 36 times bh cubed. Note that b is the dimension parallel to the axis and h is the dimension perpendicular to the axis.